of my study. Today we're gonna cover the last topic, so-called Resonant LLC or LCC converter. Um, in the next lecture, we will summarize the whole topic, what we have seen up to now, and maybe we can also solve a little questions regarding to your exam. Um, by the way, did you check the exam question catalog in the website? I prepared a few questions, and if you have any questions about what you don't understand or what's not clear is, uh, please talk about it in the next lecture. Uh, what is resonant LHC converter? Maybe just see now the whole. Okay. Hmm. It seems to be that it doesn't work. Why not? LLC means we have two inductive and one capacitive component, and this is so-called, if I copy this again, yeah, maybe it's better now, right, on the slide. This portion is called resonant 10, and we use this portion of the circuit for better efficiency, and the power range is between, actually it's more than 1 kilowatts. In the application, for example, I saw power of LLC 3 to 4 kilowatts, and the efficiency is the best with LLC converters, and the highest power density is achieved also with the help of the circuit. It's also very important to have a lower EMI. EMI is or consists of conducted and radiated parts. Uh, this is actually easy to solve. This problem is solved easily than radiated one. Why? Because we must take care about PCB layout design. And this is not easy to achieve. Usually, LHC converter operates at duty cycle of 50%, and the good thing is that we can regulate our output voltage with switching frequency. That means if you switch this circuit, this series resonant circuit, with a different switching frequency, the whole impedance is controlled or changed with the help of switching frequency. Maybe. What is the difference between series and parallel resonance? In the real applications, if you look at a normal resonant LHC converter, it's always a series converter. That means it works as a buck converter. The important point is that we switch the circuit at the resonant frequency. Switching frequency should be equal to resonant frequency. This is my input side, and this would be the output side. If we use a parallel resonance, this portion or this node is called output voltage, and in general the gain function of a converter is described as the output voltage to input voltage. That would mean that this node, the voltage at this node is important for me to have an idea what the gain is. We have seen before the first harmonic approximation. It was, I think it was on the slide. This slide is also very important. I told you that please don't forget this formula. Maybe you can write it in your sheet of paper for the exam. How do we calculate the first harmonic approximation from a DC signal to AC signal? And I will write it here, slide 46. is it? Here. Refer to slide 46 to see how we calculate the sinusoidal waveform from a DC waveform. This portion of the circuit here is actually my LLC converter, meaning that I connect my LLC converter with a rectifier in order to have from a sine wave or convert the sine wave to DC voltage. If I model it, for example, the sine voltage Vmax times sine omega t and Imax is sine omega t. And the net impedance of my source would be Vmax divided by Imax. Let's draw our sine wave. This would be the source. And the current will also look like if the load is pure resistance. What happens in the first half period of my sine wave, let's say plus and minus half wave. In the case of plus half wave, this diode D1, D2, D3, and D4 during this period D1 and the current will flow over this diode and turn back. They are conducting, they are active, and my load current, I load, will equal to ripple voltage, ripple current. This is my AC portion plus the average we assume that the output cap is very big. That means the I ripple, if the output cap is very big, AC portion of this equivalent will be smaller. And what happens during the negative portion of the sine wave? In this case, the current will flow over Q3 and likewise with the plus portion and here we see the output current. Actually it's not right, because if you have such kind of output current signal, that means output cap would be 0. Maybe I should draw the actual this would be maximum current of the load, and this would be minimum, and anywhere in the middle would be the average current. What I mean, this is not correct if we have a big capacitance at the output. But anyway, um, if you want to explain our average output current, this would be pi, the period is 2 pi, and the average current is actually calculated with the help of this formula. And it is 2 over pi times output current. Like the load. Any questions? Okay. The output power at the load with the resistance of DC is calculated as follows: the output voltage times my average current. And instead of average current, I write 2 over pi times I load. And what was the first harmonic approximation? We have a DC input voltage, which is shown here, and the AC output voltage, or equivalent voltage of DC as sine wave, is 4 over pi times the fundamental. Here n would be 1 for the first harmonic approximation for F, H, A. what is 4 over pi times dc or divided by approximately pi is this max value is this, the whole thing. This is an approximation, that means it's not really the real case in the real application, but mathematically we can define the relation between input and output by using first harmonic approximation. And we said that in the input stage of my circuit, the full circuit, I use LLC converter. And this whole thing, I can show this circuit as a sign or as an alternating resistance. That means it would be maybe this portion, the first, second, and third stage of my circuit was here. One, three. And now I will use, instead of the fourth stage, a unique resistance. It's called, this would be the full circuit will be shown as the output voltage divided by my current, and instead of I of load, this is also load, if I want to write P times pi P times pi divided by 2 times, and I put this equation here and I get this portion. What does it mean? I can define my output resistance, DC resistance, as AC resistance. If I multiply my DC resistance with this constant, this is a constant value of the formula, and the AC resistance is changed with the output load. This is my output load. What is an output load? in the real case, for example, a microprocessor. Microprocessor doesn't have a constant um, doesn't have a constant load model or an LAD. Any questions about anything, how we calculate it, or okay, let's go further with the resonant LLC converter. We said that it consists of um, four stages. The first stage is our switching switching phase, and the second one is our tank, because we save our electrical or magnetical energy in our inductive and capacitive component. And the third one is our transformer that steps up or steps down our output voltage. And the fourth one is our rectifier. Maybe we can use also here a little portion of inductance, but it's not necessary. And this would be our, in this case, AC filter. It's a second order AC filter. We are generating a square wave from here to excite our LHC resonant tank. And this resonant tank produces actually a sine wave at the input terminal of our transformer. Let's say here, sine wave voltage is produced from, a DC voltage. That's the main idea with resonant converters. And then at the output we have also the same sine wave scaled up or down by our turns ratio. This would be also a sine wave. And this signal here is actually this signal. This is the output of transformer. And we have two options in the switching phase. Um, Either we can use full bridge or we can use a half bridge. And this is called half bridge. If you use half bridge instead of full bridge, uh, 2 over pi times the DC voltage is available at the output. That means at this node, I have the half of my input voltage. I chop only the half voltage of my input and give it to my LLC resonant tank. And this would be if I use first harmonic approximation. So I have DC voltage here. By using my switches, I produce DC voltage, and I use first harmonic approximation. Then I would say I have now a sine wave at the input of my LLC tank. What happens if I excite my LLC tank with a sine wave? That means the current flows in this direction during the positive half wave, and then again um, it goes back to the source. I didn't show it here, but um, these two switches shouldn't be turned on at the same time because I don't want to short out my input source. If I turn my upper switch on, the current will flow in this direction. And maybe I should show it here. Um, let's say um, high side switch, low side switch. turn high side switch, and then turn off it and turn on the low side switch with a fixed dead time. This is dead time, and we said that we should generally use a duty cycle of 50%, and this would be from here, let's say DT, and this would be T. What happens during this phase? High side switch is on, the current flows in this direction. And I turn it off during the second phase. These two switches are off, and in this case my inductive element tries to discharge and current flows again in the same direction, but I have here anti-parallel diodes, and the current flows back again to discharge my inductive element. This is the case of mode 2. Any questions? I should maybe erase them, not to fall into misunderstanding situation. In the third mode of my switching pattern, high side is off, low side is on. That would mean in this case the charge cap will be discharged and the current will flow in the opposite direction, like this. And also during my dead time, that means both switches are off and the current cannot flow in this direction. This is off, this is also off, but in this case the current will flow into my source and comes back again to discharge the reactive component. And then the same whole thing will be repeated. I should also
Can you show one more time the current flow in phase 1 and 2?
in phase 1, this is on, this is off. That means current is flowing in this direction. And if I switch off, there is an energy stored in this inductive and capacitive component. That means the current, the polarity will change. During the mode 1, the polarity plus was here on this side. Now it's on this side. That means the current wants to flow in the same direction, and it will flow because this is also off, and the only path for the current flow would be this. I wait for a fixed time of, let's say, microseconds. That time for microseconds to discharge the energy on this component. And during this time, the energy on the inductive component will be discharged. And then I turn it again, the lower side of the switch, and this is also off, and in this case the current flows back is it clear?
Yes.
So now we have a sine wave here, this is my um, voltage on the primary side here, and I will scale it with my turn ratio. The question is, um, we have boost, buck boost converter. Uh, the resonant LLC converter is actually a buck converter. Why? Let's draw here a buck converter. Buck converter has a switch at the output, and output filter and a load. And the LLC converter is actually the same. How? We have a DC input voltage, and we have an upper side, high side switch, and then we have also a low side switch with a anti-parallel diode. Up to now, they are the same. That means LLC converter would also use or derive from buck converter. And here we have an inductance, but we call it resonance inductance. And let's show this portion not here, or okay, we show it here. It's like static. If you look back to static converter or zeta converter, you will see a coupling, DC coupling element here. And this is called resonant cap. And then I have a transformer. I showed this transformer model yeah, I forgot to mention here. I had a DC output resistance and I transferred this part of my circuit as AC resistance. And now it looks like this. I don't have any rectifier or output cap. I just only have an AC resistance at the output. And if I multiply my AC resistance with the turns ratio, square of my turns ratio, then I get this portion. Now my whole LLC converter model looks like that. It's just a resonant, inductive, and capacitive component plus an output. And I use it here, where, here. Just applying, how do we call it, the resistance of R. Let's say this should be called as rectified or let's say reflected um, load resistance into the primary, or reflected resistance of the secondary transformer into the primary. And I just have a parallel cap connected to my load here, as in buck converter. It's just a series cap here. Why do I use a cap in series? I can block DC current or signals. And by the way, because I have, I should also draw here my transformer. Let's say transformer is here. I don't use this portion, there is a transformer here. And if I don't use a series cap here, it would saturate my transformer. That means using this cap helps me to protect transformer from what?
Saturation.
Yeah. But basically, it's a buck converter. A little break, and maybe a little bit infos about the gain, the transfer function of the whole system. We modeled our LLC converter with a sine wave at the input and the resonant tank and the output load resistance. Um, maybe it's a remote. LLC converter is essentially the frequency frequency controlled voltage divider. What do we mean by saying this? This is my output voltage, and we said that the gain is actually maybe we should write here instead of DC or here input voltage. The gain is the whole steps that are individually taken the gains of the individual stage and multiplied it with each other. Output stage related to input stage. And by just changing the frequency, this is my switching frequency, we can control the output voltage. What happens if the resonance frequency of this tank 2 pi times A resonance times C resonance. And if our switching frequency that is used likewise in our sine wave is equal to resonance frequency, that means um, switching frequency is equal to, excuse me, don't write it here. Yeah, if this would be the case, then this circuit will look like this. This is our reflected resistance. This is a shorted form of resonant tank, and the output voltage would be equal to input voltage, or let's say inverted voltage. And the gain is 1. This is the purpose of the resonant tank. We should switch our circuit where our resonant frequency is. And let's look at the transfer function of each stage. If I want to calculate the output voltage of my inverted, this is stage 1. Stage 1 was our switching phase. This is phase 1. It's just the output voltage of the first harmonic approximation to our DC voltage, 2 over pi. Where does it come from? 2 over pi. Um, this is for half bridge topology. 2 over pi was our sine wave output voltage at this node here. And if we divide this voltage, or if we calculate the gain transfer function related to output to input voltage, then 2 over pi would be 1 over 2 over pi. Excuse me, 2 over pi, yeah. 2 over pi, 2 over pi times DC voltage divided by DC voltage would give us 2 over pi. This is our gain. For the second stage, the output voltage, this would be this node, the output voltage of the tank divided by the input voltage of the tank. They are all have the same character. They are all sinusoidal waveforms, but just by changing the switching frequency, the impedance of the tank changes, and the gain is controlled by changing the switching voltage. It's the output voltage divided by input voltage of the tank. And then the third phase, what was it? It was the relationship between the output voltage transformer and the input voltage of the transformer is just controlled by turns ratio. And gain is controlled by a turns ratio. That means we write all these parameters here. Let's look at the fourth phase. This is the output voltage of rectifier divided by the input voltage of the rectifier. Would mean that the output is DC, input is AC. And this is DC. The input voltage is a sine wave. And this is just pi over 4. We know that we refer to slide 46. In this case, yeah, we made a mistake. Let's just use our slide 49. This formula for the half wave or this formula for the full wave, full bridge, and this would be slide 49. This is just the coefficient of the formula. And we put it here, and the whole gain is available now. We said that LSC converter is a frequency controlled voltage divider. Maybe show it again. Our resonant this is our magnetizing inductance and our transformer. And maybe just write detected resistance, and this would be our Magnetizing inductance belongs to transformer, but this ratio is the output stage. Output state is shown with only reflected resistance, like here, this portion. We don't show it again with transformer plus AC resistance, just with unique reflected resistance. And this was our first harmonic approximation illustration. And our gain this is output voltage is a combination of series tank and the magnetizing inductance parallel to our output load. The impedance is total impedance is that this portion and divided by our input voltage. Maybe just show also this portion. This is our series tank, and this is our parallel, let's say, load impedance. And this is just paralleling reflected resistance and magnetizing inductance. The total impedance is just series impedance plus by changing our switching frequency, we change this impedance, and by the way, we change also the output voltage of our load. There is an important point here. Let's say this is 1. This X is called gain axis, and this X is our frequency axis. if you look at in the circuit from here, we see that our full circuit is always or has uh, always an inductive um, character, because if we switch, if we use a switching frequency equal to our series resonant tank, this will be shorted like here, and the rest of the circuit would be like this. And this has an inductive character. Um, this is good because um, as we see here, if we switch above our resonance frequency, let's say this is also a resonance frequency of our circuit, if we switch above this value, this area here is called as inductive region. And inductive region has the advantage of zero voltage switching. Uh, if we switch below our resonance frequency, this is this area and called as capacitive region. And we have a problem if we switch our circuit in this region. There would be a short circuit between high side and low side FETs. And high side and low side FETs shouldn't be turned on or off at the same time. For this reason, we always switching frequency should be either equal to our resonance frequency or greater than that. Any questions? Maybe summarize it here. In this case, this would be inductive. We have three options, or we switch at resonant frequency. This is also inductive because this portion cancels each other. Let's show it like this. And input would be equal to output voltage. And third, if switching frequency is equal to resonance frequency, that means the capacitive portion impedance would dominate the whole circuit, and this will be capacitive. This is okay, this is okay, but this is not okay. Any questions?
Why are there two regions where it's resonant, or the two FR1, FR2?
Actually, um, they are the same. It's just an illustration of if we switch um, we show anywhere the quality factor. Where was it? Not here. Maybe in the last lecture. There was a quality factor. Quality factor of our circuit was like this.
Mm-hmm.
And this is constant. Because if you solder the components on your PCB, you cannot change L and C. But the load changes. And this load could be microprocessor or LED or any load that has not constant that is not constant um, load, let's say. If this changes, um, the gain will be changed.
Uh-huh.
This is our
Okay.
circuit, and this is our load. And these are fixed components, these two, but this is variable. And what happens, this was our input voltage, first harmonic approximated voltage. And if the load changes, the output voltage will change. And in order to have maximum gain, I must change my switching frequency. That means these are my actual switching frequencies depending on my load. If the load uh, goes down, that means resonance frequency of the whole system will go down, and I can only switch the circuit where um, where the inductive region, zero voltage switching, is available. Let's say this is the light load case. For example, um, 1 kilo ohm um, output current will be less, and I'm still, let's say, switching at this resonant frequency. In this case, I would have gain of 1. But
Hmm.
if I reduce my switching frequency below this value, I will see that my gain rises, and reaches the maximum here. And if I go further, because um, it depends on me, the switching frequency depends on me. If I go below this value, I will see that, now my gain goes down. I lose my gain. And in this case, the current waveform, this current waveform will change. It will not be like, um, in the best case, I will have a sine wave of my output curve. If I switch at the resonance frequency. If I don't switch at the resonant frequency here, for example, here, my current will look like this. It's not anymore a sine wave, it's distorted. Then I understand, okay, I am in the false region. I must change my switching frequency again. In this region, in the inductive region, my current looks like this. Not exactly, but um, let's say this is my input voltage, and current will look like this. Current in inductive region, so at inductive region, current lags. That would mean the current will come after my voltage, and will look like this. This is what I want. Um, Let me show it already here. At capacitive region, I maybe show it a little bit all. I should use another color, but how? The current now leads, and show here this is my current, output current at capacitive region. And that would happen in zero current switching. The diodes, the two diodes, will be hard switched, and they will cause a lot of AMI problems. and the efficiency will go down. For this reason, I want always to stay above my either equal or above my resonant frequency. And this peak, maybe you see here a peak. This is a quality factor, for example, Q, let's say 1. And we have a second quality factor here, Q2. Here, Q3, let's say Q2 with another load resistance. And here, Q3. And if we combine the maximum points of different quality factors, we can define our curve where our capacitive region or inductive region. This is our border and depends only on our load because these two components are fixed, they are constant. And if we want to design, make a design, for example, oops, no. Design of aim is again we transfer our power from high voltage to low voltage buck converter. And what was the main important or key important parameters, let's say key design we said that here we have the best efficiency. That means efficiency is very important. If you want a circuit that should have a high efficiency, then you should use, for example, LLC converter. And power density. These two parameters efficiency and power density. Then we should use LLC converter. And what is also important in this design, let's look at again to our circuit. We have MOSFETs at the first stage. That means we should use maybe a transistor, a MOSFET with low RDS on. These MOSFETs at the stage 1 should have less RDS on, and at the output We have also output capacitance, let's say drain source capacitance. This should also be less. And second stage, resonant tank. In the real application, we have a little bit series resistance of our inductive component. That means it has also a little bit, or it's a loss. It has losses. How do you call it? P loss of our inductance should be also small. And the cap has also ESR value. This should be also a very small, has a small value. What else we can say? I think they are the main factors, the series resistance of inductance and capacitance. And in the third stage, magnetizing inductance maybe, depending on the current that flows on magnetizing inductance, we should select, let's say, this equation, magnetic inductance divided by resonance inductance. It's also important to have different gain. It would look like this. Or gain curve will change if we have different ratio between magnetizing and resonance inductance. And of course, the turns ratio. It should be not very high. It should be also very low. For example, uh, from 3 to 1 to 5 to 1. Turns ratio should be between 2 and 5, like this. And the last but not the least, the fourth power stage rectifier. You can use for less efficiency, you can use silicon diodes, or for high efficiency, we can use SiC diodes. This was for a design of LLC converter. And what else we can say about it? The toughest part of LLC converter, it requires the hardest design, because if you use flyback or buck boost, sepik, it's less easier. It's much easier if you compare it with LHC converter, because this resonance, this idea to operate the circuit at resonance below or above, it's very sensitive because your load changes simultaneously. It's not constant. If you connect the microprocessor with 5 volts, for example, the microprocessor requires different output currents. And this curve changes very fast. And it's not easy to switch MOSFETs at the resonant frequency. That would mean that you will switch into capacitive region and then come back again in the inductive region, and so far you would have hard switching phases and soft switching phases, and it will change very dramatically. It's not easy to use LHC converter. So this was actually the last words from me about LHC converter. Do you have any questions? In the exam, I will not ask actually the LHC converter. It will be out of our topic. But with this, yeah, what is all?
Sorry, I meant to make the laughing emoji
Okay.
because we just spent 15 minutes on it.
Yeah.
Nothing. All good. But thank you for clarifying.
Yeah, you're welcome. So we will meet again in 2 weeks, face to face, and we will make a summarize from the beginning up to LHC converter again. So thanks for joining today to the lecture, and I wish you all the best in 2025, and see you soon in 2 weeks.
Thank you.
Bye-bye.
Cheers.
Thank you. Bye.
Ciao.
Dobrze, cześć.